Okay, we're going to start looking at electric fields now. Now, electric fields share some very, very similar properties with gravitational fields. So if you haven't watched the gravitational fields videos yet, I recommend going and watching them first if you're not up to speed with them. But we're going to have a look at the electric fields, the similarities and a lot of the differences as well, because there's not a huge amount of differences, but there's a lot of similarities. So let's start out with one of the main similarities, and the fact that there is a force that interacts between two charged particles. So I drew this very same picture before, and for example, in this case, when we get an attractive force, we have to have a positive charge and a negative one. And the force of attraction between those two is, as you would expect, directly proportional to not the mass, but the charge of one of them times by the charge of the other. So we could call this Q1 and Q2, and we'll call this Q1 and Q2. So what we've got here is we're saying that the force of attraction between these two is directly proportional to the product of the charges. And as you would suspect, it's also inversely proportional to the square of the distance between the 2 point charges. Again, sometimes you do have charged spheres that are bigger than singular points, especially when we deal with larger charged objects. But so for all intents and purposes, the distance r is the distance between the centers of those two charges. So we can now come up with a new equation for this, and this is not Newton's law, this is Coulombs law. So F is equal to K Q1 Q2 over R squared. And this is Coulombs law. And that basically suggests that the force of attraction in this case is equal to the charge times by the charge times by a constant K divided by R squared. Notice how this is very, very similar equation to Newton's laws, which is Gm over R squared. Notice how similar those two equations are. So the force of attraction between these two masses, between these two charges, is based on this equation here. Notice that we're not using G anymore, we're using K. We'll come to K in a second. So, time for one of the first differences. What happens when I turn this into a positive charge? Well, as we well know, two like charges do not attract, they repel. This is the first difference between gravitational and electric fields. The fact that in gravitational fields, we only have attractive forces, whereas in electric fields, we have attractive and repulsive. And this is an example of a repulsive force. So in this case, we would expect the force to be repulsive. And fear not, there's not any other equation, it's still the same equation. Everything is the same about it. It's just instead of this being an attractive force, it's now a repulsive one. So this is Coulombs law in action. And again, it's very, very similar. But now we want to spend some time and actually see, why does a positive and a positive charge create repulsion, and why does a positive and negative charge create attraction in terms of the fields that are interacting? Well, we can draw the fields just like this. And here comes difference number 2. Hopefully you spotted the difference that I've drawn the arrows going outwards. That you might think is quite peculiar, Whereas in the gravitational fields, we had the arrows pointing in the direction a mass would travel because it's always attractive. Well, in this case, it's not about mass, it's about charge, and we define these field lines. Their direction indicates the direction of a positive test charge. So if I was to put a positive testing charge in there, it would move in that direction, and that's why we do this way round. It's just a convention that we've all stuck to and we're always going to stick to. So this is the way you should remember it. The arrows are drawn so that when a positive charge was placed in that field, it would move in the direction of the arrows, which quite nicely means that if this was a negative charge, the arrows would be pointing inwards, because if you were to put a positive charge in that field, then what you get was the charge moving towards this negative. So, how do we get attraction and repulsion then? Well, it's all to do with the interaction of these fields that causes them to attract or repel, depending on what charges you've got. So we've actually nicely set up here a negative and a positive charge. I don't need the cues anymore. So how are these fields going to interact to create attraction? Well, they join together. That's quite simply what they do. Notice the field line coming out here joins up really nicely with that one. This one will join up really nicely with that one. And so on and so forth. Draw that one a bit better. And so we get this effect of the field lines joining up. And these field lines joining up effectively causes an attraction because these field lines want to shorten and straighten. And so what happens is that they pull on this object and they pull on this object to try and bring them together to shorten and straighten. So in this case, we get an attractive force. Let's change this up a little bit. So let's turn this back into a positive. So this has now got arrows coming out. What happens? Well, as you'd expect, when two arrows come together, they butt heads and they bounce off. So what we get here is we get this effect. And so as a result, because they butt into each other, we get this repelling effect down the middle. And that creates repulsion. And so now we've effectively diagrammatically shown how fields interact to create attractive forces and repulsive forces, in specific the charges that we're dealing with here. But there's more to electric fields than this, because obviously we haven't talked about field strength, how we talked in gravitational fields. Very much so, we can treat point charges as sources of charge that have a field, and we are going to deal with a positive charge this time, just to make it, just to keep it simple. So we've got our positive charge and we've got our electric field. The same rule applies. It's radial. The field strength is getting weaker and weaker and weaker as it gets further away from the point source. Inverse square law. So the further away it is, it varies with 1 over r squared. So we've got a situation here where we can actually now use the same logic as we used in the previous, in the gravitational fields, as we can now using the electric fields. So the force that a charge would feel here, let's say we've got a negative charge here, the force that this would feel is equal to K times Q1 Q2 over R squared, where this is Q1 and this is Q2 in this case. But what if we want to know the field strength? This is a force. We want to know the field strength, the same as we knew G in gravitational field strength. We want to know what the equivalent is in electric fields. So field strength for a gravitational field was a force per unit mass. So what do you think a field strength is for an electric field? Well, it's still force, but notice what did we replace charge with, the mass with before? We replaced it with charge. So it's force per unit charge. So we're saying that if we put a charge in this field at this point, we are going to get that much force because this is the field strength. The same as if we put a mass in a gravitational field, it's going to feel that much force because of that field strength there. So quite nicely, we can derive a new term for this in terms of a radial field, in the same way as we did the other one. Because F is equal to KQ over R squared, which we can then say F over Q, that's this Q, by the way, Q2, is equal to KQ1 over R squared. Well, look what we've got here. We've got the field strength. We call that electrical field strength E. And electrical field strength E is equal to KQ over R squared. And again, very, very similar to the gravitational field equation, which over here, the gravitational field equation was G is equal to Gm over R squared. Notice the similarities between these two equations. Now there's one more difference that we've not dealt with yet, and hopefully you remember what it was. It's this K term. Now, unfortunately, this is not always constant. Sometimes it changes, but not very often, because more often than not, we do deal with charges in air. Now, if we're dealing with charges in air, the value of the constant K comes out to be 9 times 10 to the 9. And that 9 times 10 to the 9 will change if we're not in air, because K has its own equation. And this is one of the key differences. K is equal to 1 over 4 pi epsilon naught. Now, hopefully you're happy with 1, 4, and pi. No problems with any of those terms. But you might be looking at this epsilon naught value and going, what in the world is that? Well, this is the permittivity of free space. It's effectively a constant that suggests how easy it is to set up an electric field in the substance that you're in, which in this case, permittivity of free space indicates a vacuum. Well, the value for air permittivity and a free space permittivity, i.e. a vacuum, is for all intents and purposes the same, and we don't tend to worry about it. But for other values, say water or paper or other values that you might be setting up an electric field through, then this value will change and a new value of K needs to be worked out. Or you could rewrite this equation to be something slightly different as F is equal to 1 over 4 pi epsilon naught Q1 Q2 over R squared. And of course, you can write the field version very similarly So we wrote the field before as kq over r squared. We can write the field version as 1 over 4 pi epsilon naught q over r squared. And for all intents and purposes, these equations you will be using regularly when you're doing these electric field questions, but quite nicely you should hopefully be able to see that they all effectively are the same thing. So very important equations, these ones and this ones, and I think one that is often forgotten about is one I derived earlier and showed you, which was the E is equal to F over Q, which actually then gives the field strength as having a unit as newtons per coulomb. Remember, field strength for a gravitational field was newtons per kilogram. So it's just important to note that there are similarities, there are differences, but the similarities will help you to remember the things you need to remember. Okay, so that's everything you need to know about electric fields so far, and hopefully this video, you can watch it again if you missed any bits and come to class with any questions that you might have.